Hey guys, I just want to talk to you about these two questions this week. Question 2 and question 4 in the 2019 AP FRQ question. Let's go to question 2 right away. Hope you're doing well. First of all, question 2. Um, when we read through it, it says the answer to the following question. The molecular formulas of three molecules, diatomic, bromine, chlorine, and fluorine, are written below. Which one has the longest bond length, and justify your terms in terms of atomic structure. So what you want to do there is you want to think about obviously the size of the atom. And if you think in the periodic table and you get down towards the bottom of the periodic table, what do you see? You see that iodine has the largest size. It has the most energy levels, it has the most electrons, and so therefore its radius is the biggest. And when you think about the biggest radius, that means it would have the longest bond length. So you'd want to make sure in your answer that you talk about energy levels and radius. The size is the biggest. When you look at question 2, you're not going to really have to deal with a question like this as far as the reasoning involved, but the idea is good. The idea is that you have three substances, and what you want to do is make this. So you want to do a reaction where you turn NaBr into somehow Br2. And you have two possible reagents, Cl2 and I2. And the idea is we know something about how spontaneous it is with this number. This is the electromotive force that it has. And we see that chlorine has more electromotive force and iodine has less electromotive motive force. So what that means is we could use the chlorine. And so the correct answer here is basically you would use the chlorine because this number is bigger than that number. And that means this chlorine could replace the bromine inside of sodium bromide and give you the bromine too. So that's the question there as we go through it. Again, you wouldn't have to use that reasoning. The questions continue. Obviously, we have bromine and chlorine reacting to form a compound BrCl2. And then look at questions C, D, E, F, and G. C is going to be about boiling points and structure. D, E, and F are going to be about equilibrium that you can see set up. And G is going to be about bond energy. So let's go through this and think about these. In C, what we have is a boiling point of this, and we're told to explain the difference in boiling point in terms of intermolecular forces present between each substance. So you got to identify the intermolecular forces in bromine. Bromine is going to be bonded to itself. It would have only LDF as its forces. Bromine chloride, though, probably has a polar covalent bond in it, and so it would have LDF and probably a dipole. But when you think about what it says there, it says explain the difference in boiling points in terms of intermolecular forces present in each substance. So first of all, for 1 point, you'd have to identify correctly what's going on. And then look what the data tells you. The data tells you that that 322K is bigger than the 278K. So that just simply tells you that the London dispersion forces are greater than the combination of London dispersion forces and dipole and BrCl2. So you would say each force, and then you would say for the bromine, the London dispersion forces must be greater than the LDF and dipole forces in bromine chloride since its boiling point is higher. Hey, let's look at this equilibrium that we have set up. We have this idea that bromine chloride, two bromine chlorides can split apart into bromine and chlorine. We see that it's endothermic. We get the delta H. We're given some information. 0.1 mole is placed in previously evacuated 2-liter container at 298 Kelvin, and we're told that it reaches equilibrium. What's the pressure before equilibrium is expressed? So you're going to have to use the ideal gas law and D, and you're going to have to use the data that you're given there, and it would simply be P equals nRT over V. You're given that it's 0.1. You're given that R is 0.08206. And you know that it's 298 and it's a total of 2 liters. When you do that work, you find out that it'll go right to and form at about 1.22 atmospheres. That's a 1-point question. Hopefully you can do that. And then, of course, writing the equilibrium. We know that we have these two products, this reactant. So we could write in terms of pressure or concentration. Let's do it in terms of concentration. So we would just say Br2, concentration of Cl2 over concentration of BrCl squared. Remember that squared on the bottom. That's what they would want for E. Again, that's a 1-point question. And then you get to an icebox problem. It says after the equilibrium is after a system's reached equilibrium, 42% of the original BrCl is decomposed. We gotta get to that icebox problem. Let me draw this icebox over here so that we can see it. And I'm gonna have the BrCl, and I'm gonna have the Cl2 and the Br2. These are at 0 initially, and this is 0.100 moles. We're told that 42% of the original sample is decomposed. So if I take 0.1 times 0.42, I'll find out how much is decomposed. And I can find out that that is going to equal, well, it's going to equal a number, obviously 0.42. But what does that number represent? Well, remember, in the icebox, we're going to see this go up by x and this go up by x. And this is going to go down by 2x. Remember the coefficient in front right here was a 2. So 1 minus 2x equals 0.4, 1 minus 2x, and this is 2x. So that means 1 minus 0.42 is 0.58 down here. X is going to be 0.21, and so this will be 0.21, and this will be 0.21. So 0.21 squared over 0.58 squared, and we get our answer 0.13. That icebox is about as hard as they'll come. This idea of using percent, it's nice to use the 0.1 and come up with the numbers. You just got to be clear on it. That leads us to G. How can we do that? I'll do G over here just so that we can see it. The idea in this one is that the total amount of energy here equals these bond energies minus this bond energy equals this number. Sorry, that moved. And so 0.16 is going to be equaling, as we can see here, kilojoules. It's going to equal 2 times that BrCl minus 193 kilojoules minus 243 kilojoules. And so when we do that, we'll see that we get our geometric, we just do the algebra here. This is 2x, and we end up with this idea that like 437.6 equals 2x. And so we get x equals to 219 kilojoules. That's the answer that would go here, 219 kilojoules. That's question 2. Hopefully you're feeling good about that, and some of that stuff goes well for you. Question 4, we talked about this one. I didn't talk much about it, but we can see students do an experiment with carbon dioxide. We know some information. We know it's 299 Kelvin, the pressure is 0.7. They decrease the temperature, and they increase the temperature to 425. What would describe the effect of raising the temperature on the motion of this particle? As you go from 299 to 425, as temperature goes up, the kinetic energy has to go up, which means the velocity will go up. The particles will simply move faster. So what would they have on the motion of them? They would have more velocity, and that's the key thing to remember there. Calculate the pressure of the CO2 in the container at 425. So that's an ideal gas law problem. And that is the pressure equals nRT over B. And we would just substitute and solve there, but hold on. Notice that in this problem, all we see is that the temperature changed. We're assuming then that the container's volume stays the same. And when we look, we really don't know the volume. So can we use the ideal gas law? No, we have to use simply P1 over T1 equals P2 over T2. So remember, we often fall to the ideal gas law, and it is the most common gas law we use. But this is called the Gay-Lussac law, and it's just pressure and temperature are directly related. And so if I substitute the numbers in 0.70, and that's at 299 Kelvin, and that equals X at 425 Kelvin, we get our X to equal 0.99 atmospheres. So it makes sense. As the temperature goes up, the pressure goes up, directly related. Why is it, in terms of kinetic molecular theory, it would explain why the CO2 in the container changes? Well, that's simply because the force and frequency, and you could probably say either one, I'm not sure, but the force and frequency of the collisions increase. As temperature goes up, obviously the particles move with more velocity, and so they'll hit the walls of the container with more force, and they'll do it more frequently. Finally, in D, it says student measures the actual pressure of the CO2 and observes that it's less than the pressure predicted by the ideal gas law. This is basically the concept of a real gas. The ideal gas law assumes that there's absolutely no interactions between the particles. They're, pointless little things. And in the real world, it seems that there's probably some forces between them, and that'll stick them together. So they'll stick together a little bit more and collide with the walls of the container a little bit less. So it's a real gas. And what that means is there must be, and there is, a small force of attraction between CO2. That's always true. The ideal gas law is just a math law that glances over that. Hey, these are the two questions that we wanted you to be good with, and I hope that you're good with these. Keep your practice up. We'll be getting in touch this week about the nature of what's going to happen with testing. We have about 3 weeks, and so hopefully over those 3 weeks we'll be successful. Take care, and we will see you soon.